This is an introductory talk in logarithmic geometry and moduli. The goal of these unordered talks is to understand why the theory of log geometry is useful in studying moduli problems. And in due course, we also aim to study the geometry of Deligne-Mumford stacks. So let's start. So the logarithmic geometry was developed to deal with the main two fundamental problems in algebraic geometry. One is the compactification, and the second one is degeneration. So one of the key aspects of algebraic geometry is that it is essentially global in nature. Now, what do I mean by that is that varieties can be compactified. That is, if you have any separated scheme U of finite type, say over a field K, then we all know that it admits an open immersion J to X, where X over K is proper and the image Ju is Zariski dense in X. Okay. Now, since proper morphisms or proper schemes are much easier to study the general schemes, so it is often convenient to use such compactification, even if the original scheme U, that is our primary interest of study, it is often useful to study such compactification. So if we are in a compactified space X, then it becomes necessary, then it is necessary to keep track of the boundary. Keep track of the boundary. So what is the boundary? It is defined as the X minus U, the original object U, which we are interested in studying, and study how functions, differential forms, sheaves, and other geometric objects behave near Z. And somehow we need to carry along the fact that it is U rather than X which we are interested in a functorial way. So we have to keep that in mind. Okay. And then how the development of the development of logarithmic geometry, as I said that it was to deal with compactification and degeneration. There were many classical methods to deal with such problems. This was originated from various classical methods which were known earlier. So one of the some of the notable theories are of the theory of toroidal embeddings, of the theory of differential forms and equations with log poles or regular singularities. Regular singularities and also the logarithmic minimal model program and Kodaira dimension. Okay, so logarithmic geometry was influenced by all of these ideas, which provides a language which incorporates many of them in a functorial and systematic way, which extends beyond the classical theory. So in particular, there is a powerful version of base change powerful version of base change for log schemes, which works in arithmetic geometry. Which is indeed the area in which log geometry has seen its most spectacular applications. So again, uh, these two problems of compactification and degeneration are related. So the compactification problem is related to the phenomena of degeneration. How? If we take a scheme U, this often arises as a space which parameterizes smooth proper schemes of certain types. So this often arises as a space parameterizing smooth proper schemes of certain type, and there exists a smooth proper morphism V to U whose fibers are the objects which we want to classify. Okay, so in good cases one can find a compactification X of U a compactification X of U such that the boundary parameterizes the degeneration of the original objects. Okay, and also there is a proper and flat morphism but not smooth from Y to X which compactifies V to U. So then we are left with the problem of analyzing the behavior of f along the boundary and comparing how is u related to x and v is related to y. So a typical example of compactification is the compactification of moduli stack of smooth curves by the, so let me write it, compactification of moduli stack of smooth curves by the moduli stack of stable curves. Okay, then what we will study is that what is actually logarithmic geometry and why it is so useful. So one of the reason we study logarithmic structures is that it fits so naturally with the building blocks of the schemes. So in most cases, in most of the cases, the logarithmic structures are the logarithmic structures are straightforward with the standard ways and intuitions of algebraic geometry. Now, let me give you an example. Uh, so, in particular, logarithmic geometry is compatible with the notions of smoothness, uh, differentials, and differential operators as well. So, for example, if x is a smooth variety over a field K and u is the complement of a divisor with normal crossings, then the resulting log scheme obtained from this the resulting log scheme obtained from this turns out to satisfies the Grothendieck's functorial notion of smoothness. Grothendieck's functorial notion of smoothness. More generally, so more generally, any toric variety with the log structure corresponding to the corresponding to the dense open torus it contains. Is actually log smooth. So the theory of toroidal embeddings this theory is nothing but the theory of studying log smooth schemes over a field. Log smooth schemes over a field. Okay. Now let's illustrate how log geometry works in the basic case of a compactification. So take an open immersion J from U to X like above. And let MUX in the structure sheaf denote the subsheaf which consists of the local sections of OX consisting the local sections of OX whose restriction to U whose restrictions to U is invertible. Okay. Now if we take two sections F and G from this, from U minus X, then Fg is also here. Okay, but their addition need not be here. Need not be in Mu minus X. Okay, thus Mu minus X, this is not a sheaf of rings, but it is a multiplicative submonoid of OX. Now note that this Mu minus X, this contains the sheaf of units of OX star, of OX actually. So then note that this is actually contained in Mu minus X. So this notion of U minus X is a little bit confusing, so let me change it to this. This is the standard notion. So now if X is integral, then the quotient Mux quotiented out by the sheaf of units, the units of the sheaf of the structure sheaf, is just the sheaf of anti-effective Cartier divisors on X with support in the complement Z of U in X. with support in Z, which is the complement of U in X. Okay. So by definition, the morphisms of the sheaf of monoids the uh, the morphism which is inclusion of sheaf of monoids uh, alpha ux from mu mux to ox is a logarithmic structure. Which in good cases this remembers the inclusion from u to x. Which remembers the inclusion from u to x. So more generally, if x is any scheme and then a log structure on X is a morphism of sheaves of monoids of commutative monoids alpha from M to OX, inducing an isomorphism from the preimage of the units to itself. Okay, so this is how we define a log structure. We will see, we will elaborate this notion of definition maybe in some future lecture. Yeah. So let's see a more bit of history of when it was developed. So the foundations of this theory was first given by Kazuo Kato of this theory was given by Kazuo Kato Kazuo Kato, and it was more developed by Fumihiro Kato after that. So it was developed following the ideas of Fontaine and Iluse, following the ideas of Fontaine and Iluse. Yeah. So the main body of the main body of work on logarithmic geometry has been concerned with deep applications in the cohomological study of periodic and arithmetic schemes. So then this theory had an importance of an yet another extremely complicated theory, but the treatment of this theory are however quite accessible. Now the aim of this talk of the series of talks is to is to convince the reader that uh, the theory is very simple enough to be considered by anybody who is interested in the moduli of singular varieties or or in moduli problems arising in arithmetic geometry or number theory. Yeah.